Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll describe the steps of null hypothesis significance testing, or NHST, in detail. We are going to learn the general steps of NHST that are used for many of the statistical tests. These are the steps. State the hypotheses, set the criteria for a decision, compute your test statistic, and finally, make a decision about significance. The first step, after you have your research question, is to state the null hypothesis. Remember that the null hypothesis is a statement of equality. Depending on your research question, your null hypothesis may take on different forms. The first example of the null here is that the mean of group 1 is equal to the mean of group 2. The second example of the null is that the mean is equal to 0. The third example of the null is that a population mean is said to be equal to a particular number, for example, 10. That's a null hypothesis too. It's a statement of equality. These are different types of null hypotheses that would require different types of tests. In step 1, you also state the alternative hypothesis, denoted as H1. Remember that this is a statement of inequality. The first example of an alternative hypothesis is that the mean of group 1 is not equal to the mean of group 2. This is a non-directional hypothesis. The second example is that the mean is less than 0. This is a directional hypothesis. The third example is that a population mean is said to be not equal to a particular number, for example, 10. This is also a non-directional hypothesis. After you state your hypotheses, you need to set your significance level. I discussed this concept in the last lecture. Your significance level is the probability of type 1 error that you are willing to accept. In other words, this is the level of risk you are willing to take that's associated with incorrectly rejecting the null hypothesis. Because we never really know what's going on in the population, which is what our null refers to, we have to take some risk that we are wrong in our decision to reject or retain the null. So we are setting our alpha. As we discussed last time, we usually set alpha, or the significance level, at 0.05 or sometimes at 0.01. If alpha is 0.05, the probability that the value associated with your critical value or greater will occur 5 times out of 100 if the null hypothesis is true. You could use 0.01, but as we talked about, this will inflate your type 2 error, the error of not rejecting the null hypothesis when it is false. Remember, there's a trade-off between type 1 and type 2 error. If you think about it, the stricter the criterion you set for rejecting the null hypothesis, that is, the smaller the alpha level, or in other words, lowering the probability of getting a false positive, the more likely it is that there will be cases where you should reject the null hypothesis, but you don't, or you get a false negative. Step 2 is to select a rejection rule. A rejection rule requires determining the critical values associated with the test. We're figuring out what values are needed to reject the null hypothesis. This requires us setting the significance level and also knowing the sample size. The rejection rule will have one of 3 general forms. We'll either reject the null hypothesis if the absolute value of the observed value is greater than or equal to the critical value. This would be a non-directional rejection rule. Or we would have a directional rejection rule. So we'll reject the null hypothesis if the observed value is greater than or equal to some positive critical value or less than or equal to some negative critical value. So to fully understand the rejection rule and what it represents, I'm going to take a short detour to explain the rejection region and critical values and 1 versus 2-tailed tests. So let's talk more about what we are really doing when we state the rejection rule for step 2. In this framework of NHST, we have decided that we are going to reject the null hypothesis if we obtain a value in our sample that would be really rare to get if the null is actually true. When we set our significance level, we decided how rare the value would need to be to convince us that the null isn't true. By setting our significance level at 0.05, we said that seeing a value that would only occur 5 out of 100 times given the null was true would be enough to convince us. Looking at the sampling distribution of means here, values close to the null value, which is 0 in this case, are pretty likely to be observed if the null is actually true. Values far from the null are much less likely to be observed if the null is actually true. Those rare values in the tails, the sections in blue, will form our rejection region. What is a rejection region? They're values on the sampling distribution that have a probability equal to or less than alpha if the null hypothesis is true. So the area under the curve in the rejection region needs to total alpha. Here we have cut our 0.05 significance level in half to be 0.025, so the rejection region is equally distributed at either end of the distribution. Again, the blue parts of the distribution represent extreme scores that include low probabilities of the score occurring by chance if the null is really true. This rejection region is associated with critical values of z. Our critical values of z in this example are positive or negative 1.96. So this rejection region is associated with certain values of z, positive or negative 1.96. And we need to know what precise values we would need to see for us to conclude that our sample's mean does in fact fall into the rejection region. That's where critical values come into play. Critical values define the boundaries for the rejection region on the sampling distribution. Critical values are our criterion values for rejecting the null hypothesis. Essentially, if your sample's statistic touches or exceeds the critical value cutoff, here, those z values, you are in the rejection region. Your value would be rare if the null were true. Now let's talk about one versus two-tailed tests. A two-tailed test just means that we have rejection regions on both sides of the distribution, like the example on the previous slide. For a two-tailed test, we divide the area under the curve corresponding to alpha in half to put an equal amount below and above the mean. Two-tailed tests are more common than one-tailed tests. This is when we have a non-directional alternative hypothesis. That's when we do a two-tailed test. So for example, if we think that our mean is just not equal to 0, but we're not sure if it's higher or lower, then we have a two-tailed test because we have a non-directional hypothesis, alternative hypothesis. If you have a directional alternative hypothesis, you could do a two-tailed test, but you don't have to. A lot of times when we have directional alternative hypotheses and we're sure that we're going to see an effect in one way or another, either positive or negative, but not both, we do a one-tailed test. So for a two-tailed test, the rejection rule is that we'll reject the null hypothesis if the absolute value of the observed value is greater than or equal to the critical value. This allows us to look at either the positive or negative observed values for the two-tailed test. For a one-tailed test, we put all of the area under the curve corresponding to alpha just on one side of the distribution, and the side is chosen based on your alternative hypothesis. If you have a non-directional alternative hypothesis, you can't do a one-tailed test. If you have a directional, you may. You could also do a two-tailed test, but typically we do a one-tailed test. So for a one-tailed test, the rejection rule is either, depending on the sign of your directional alternative hypothesis, is either that you reject the null hypothesis if the observed value is greater than or equal to some positive critical value, or we reject if the observed value is less than or equal to some negative critical value. So if it's either more extreme, positive or negative, than the critical value. Notice that you can't change from a two-tailed to a one-tailed test after the fact. That's considered cheating. You might make it easier to reject the null by moving the critical value closer to the middle of the distribution. We just covered step 2, stating a rejection rule for when you do the analysis by hand. But step 2 is different to select a rejection rule when you do the analysis by computer. There's no need to find critical values. The computer will find them for you. And then the computer reports the exact probability, or the exact p-value, of your observed value. And then you compare this p-value to the significance level that you set, typically 0.05. In this case, on the computer, your rejection rule will always be reject the null hypothesis if the p-value that the computer reports is less than or equal to your alpha that you set, typically 0.05. I'll talk more about p-values in a minute. Step 3 is to compute the test statistic value. The result is also called your observed value or your computed value. Again, we'll cover how to compute different test statistic values later for the remainder of the semester. Step 4 is to make a decision by applying the rejection rule. So this involves comparing the obtained value from your test statistic, or the observed value, to the critical value. The obtained value and the critical value are compared to make this decision. Remember, the critical value is the value defining how extreme the sample value would have to be for it to be too unlikely you could get such an extreme score. Another way to think about the critical value is that these are the bounds of the rejection region on the sampling distribution. If the observed value is equal to or more extreme than the critical value, you decide to reject the null hypothesis. The more extreme just means more negative if the critical value is negative, or more positive if the critical value is positive. That is, it's farther into the tails of the distribution. If your observed value is more extreme than your critical value, it indicates that the value you obtained in your statistical test likely was not obtained due to chance. Its occurrence was statistically rare enough, in other words, it had a low enough probability if the null were true, that it likely was not due to chance. If we decide to reject the null, this means we are rejecting the equalities in our null hypothesis statement. On the other hand, if your obtained value does not meet or exceed, in other words, is not more extreme than the critical value, then we decide that we retain the null hypothesis. It means that it's possible that the differences we observed may be due to chance or something that is out of the researcher's control. If you're computing the test statistic with a computer program, which you'll learn how to do in this class, the computer reports the exact probability or p-value associated with the statistical test. The p-value is the probability in any one test of observing data at least as extreme as that observed, given that the null hypothesis is true. In other words, if the null is true, what's the probability of getting a value as large or larger than mine? If you're using a computer, there is an alternative to the last step. That's when you compare the probability value to your alpha level. And if the probability value is equal to or less than your alpha level, you reject the null hypothesis. Let's revisit statistical significance. If the observed value of the test statistic meets or exceeds your critical value and falls into the rejection region, those blue or green regions in the figures that I showed, you have a result that is statistically significant. Alternatively, if you are doing an analysis by computer and your p-value is less than or equal to alpha, you have a result that is statistically significant. Non-significance is when the observed value of the test statistic does not fall into the rejection region, or when p is greater than alpha. That's when we fail to reject the null hypothesis and determine that there is no statistical significance. Note that APA, when we report these, prefers us to use the term non-significant as opposed to insignificant. This concludes the lecture on NHST steps. In the next lecture, I'll describe the concept of inference in our course framework.